All right, so welcome everyone. Thanks for coming to also our new semester in a new room in a new building for the CSC seminars. So glad everyone found their way here. Very pleased to have for the first speaker of the term, Professor Lexing Ying from Stanford University. Lexing is a professor of mathematics at Stanford. Prior to his time at Stanford, he spent some time on the faculty at UT Austin. And prior to that was a postdoc at Caltech and then did his PhD at NYU. And Lexing works in a really huge variety of topics, sort of in scientific computing, numerical analysis, but with applications ranging now from machine learning to chemistry. And won a number of awards along the way, the Sloan Fellowship, NSF Career Award, the Wilkinson Award from SciAm, and has been an invited speaker at the National Congress of Mathematicians. And is today going to tell us about just a small fraction of things he's been doing on. So welcome, Lexing.
Thank you, Joseph. Thank you very much for the introduction, and thanks a lot for inviting me here. And the new building, and well, we'll see how it works. So today I'm going to talk about some new stuff I've been thinking about recently. It's called eigenmatrix for unstructured sparse recovery. So I choose this topic. Part of the reason is because it's a topic which is kind of suitable for broad audience because it doesn't require too much background. But the other thing is that there are a lot of experts here at MIT has been working on similar problems. So here we go. So the problem we're trying to address is this so-called unstructured sparse recovery problem. So let me just give you the abstract set of the problem for a second, and then I'll give you a few examples. So X denotes for a parameter space. So this absorbs it, but anyway, I can point at my fingers. X is a parameter space, so you can think about this as a as you will see, you can think about it like an open setting in complex plane, or maybe like it's just an interval. Okay, it's control the parameters of the problem. Now S denotes the sampling space, and we use a capital S to stand for the sampling space. And the third thing we have is we have this kernel called a GSX. So it's a function with two parameters. The first parameter is the location where you're going to perform the sample, and X is the parameter. Okay. So we make an important assumption, as you will see, is that this function Sx is analytic in the second variable x. It's analytic in the parameters. And so the main player in this talk is going to be this unknown signal fx, which is the sum of a bunch of deltas. And these deltas are sent at the location xk and also with weight wk. Okay, so we don't know the location xk and we don't know the location and the weight wk. But we do know that it's only a small number of sums. So that's why it's a sparse signal. Okay. And sometimes you know how many spikes you have, and sometimes you don't. And we need to figure out the number of spikes. Now, we don't know the signal fx, but on the other hand, we can access some of its information through this kernel G. So we define this function us to be the integral of the kernel gsx and multiply fx and take the integration over the whole parameter space. So now, because fx is the sum of the deltas, you can just write this integral as a bunch of sums. So this is the sum of this kernel G, evaluate the location S with a spike at xk and weight xk. Okay. Now, unfortunately, we don't get to access this this signal everywhere. We can only look at the signal information at a bunch of points, which will be denoted by Sj, j from Sj equal to 1 to ns. Okay, and more importantly, we will not make any prior assumptions on the locations of these Sj's. We'll just assume them to be some unstructured sample locations, which was given to us, and we cannot do too much about it. Okay. Now, the problem is that given some approximation, which denoted by uj, which are approximately equal to this observation function u at the location Sj. Okay, so in the ideal case, this will be equal. You would just see the function u at Sj. But what if you have noise? Then it will be a noisy perturbation of USJ, and this is what we receive. And the task is to, from this uj, what we want to do is that we want to figure out what the location xk's are and also what the weights are. Okay, so this is what we call an unstructured sparse recovery problem, because we want to recover a sparse signal and based on some observation at unstructured point locations. Okay, so this is rather abstract. Let me just give you a few examples. So the first example is so-called it's called rational approximation. So here you can think about X as to be an open set in the complex plane. So two typical examples are the disk or the half plane. So here I'm drawing a picture of the disk. So X is is a space where my parameters live in. So S, the space of the observations or samples, will be a complement of it. So it would be typically where you require the points to be a little bit separated away. But I mean, in this simple case, you can just think about S to be the complement of the complex plane with respect to this parameter space X. The kernel G is take two parameters S and X. It's very simple. It's just 1 over S minus X. And the unknown quantities that we want to recover are the spike locations and also the weights. And the Sj is a bunch of points. This denoted by the color yellow here outside the domain. Okay. And well, plugging these formulas into the definition of Uj, and you will see that Uj is a noisy approximation of the sum of these spikes with this kernel 1 over S minus X. Okay. This is the first example. So this is an important example. So typically, suppose you have an analytic function outside a certain domain, but you know that it's actually coming from sum of a bunch of poles. By observing this analytic function at these yellow locations, what you want to do is that you want to figure out the pole locations and also the pole weights. Okay, so that's called a rational approximation. The second example, which is a special case of rational approximation, but it's play a very important role in condensed matter physics, is something called a spectral density estimation. So here, the X is not the disk. It's just really in an interval on the real line. It's from minus B to B, where B is some parameter was given to you. And S, the sampling space, is actually only part of the complement. It's actually only on this imaginary axis. Okay. And the kernel is the same, is also 1 over S minus X. And the unknowns will be these red poles in this interval from minus B to B, and also the weights associated with them. And what are the locations for samples? This actually comes from is a part of this so-called Matsubara grid. So these are the grids given by this form. It's 2j minus 1 times pi I divided by beta, where j goes from 1 to a certain integer, which I denote by ns. So ns is actually contain how many yellow points you can sample. This beta is the inverse temperature, which is 1 over the temperature T, and is really decided by the problem, the physics problems. Now, the observation is again the same. It's summation of Sj minus Xk times Wk. So it's a special case of the previous problem, but now this problem itself has very important physical meanings. So that's why I listed it separately as a second example. So in fact, my work is really motivated by this example. I started looking at the problem about 2 years ago, and then eventually leads to this, what I'm going to tell you today. The third example, which I called, is called the Fourier inversion. This is really a very common example. So here you see that the X is really the frequency space. I apologize. Typically, X is denoted by the spatial domain, but in order to have a uniform notation, here X you can think about it as actually the frequency. So the frequency from minus 1 to 1. S, the sampling location, is actually corresponding to this real line. And the kernel is very simple, just a Fourier kernel, exponential of pi I s times x. So the frequency is denoted by x, and the location at that time, you can think about it with the sample is corresponding to s. Now, we are allowed to sample at a few locations on the real line. And the signal is actually, because this is the sparse signal, so therefore the signal is actually corresponding to plane waves which are associated with a few frequencies. So here I showed you one high frequency wave and one low frequency wave. And what you observe is actually a weighted superposition of them. You get to see the signal at these yellow points. And what you want to do is you want to figure out the frequency and also the weights. Okay, so this is the Fourier inversion problem. The next problem is also very similar. It's called Laplace inversion problems. So here, what you have, the kernel is not the oscillatory Fourier kernel, but you have this decaying Laplacian kernel, e to the minus sx, where s control the decaying parameter. Oh, sorry, x controlling the decay rate. So we assume that x is from 0 to a. Okay, I cannot work with things which decaying too fast because immediately it collapses to 0, and you can't discover that. So therefore, you have an upper bound about how far it decays. Now, S is corresponding to the sample locations. These are points on the real axis. And the signal you receive is actually a linear combination of a few decaying modes. Some of them decaying quite rapidly, some of them decaying quite slowly. And by observing the linear combination of these modes at a few points, you want to figure out what is the decay rate and what is the weight. Okay, so that's the Laplace inverse problem. And finally, we have this so-called sparse deconvolution problem. So here, what you can think about is that your parameter space is actually on certain interval is control the center of these bumps. And the kernel is some translation invariant kernel, which, for example, you can think about this is one of the examples given here is this Cauchy kernel. And what you observe is a convolution of this kernel with a few delta functions. And you get to observe them at few locations. And what you want to do is that you want to figure out the center. And also you want to figure out the weight. Okay, so this is the last example. Now, so here I give you 5 examples. Hopefully I convey I convince you that this is actually an important problem and has many, many applications. Now, there's a long list of work on this unstructured sparse recovery problem. And in each of these examples that I give you, there's a long history and many, many important work. For example, in the case of rational approximation, even recently, in the past 20 years, there have many algorithms being proposed for this. And some of the names associated with this is RK-fit, barycentric interpolation, vector fitting, Padilla approximation, and AAA algorithms. A spectral function approximation is actually this example related to Matsubara grid come from condensed matter physics. Actually, also has a very long history. So some of the famous methods has been proposed, including Padilla approximation, maximal entropy methods, stochastic analytical continuation, and recently we also contributed to this effort. Fourier inversion is probably the most important example among the 5 because it associated with many very important names in signal processing. So for example, if your frequencies actually come from uniform grid and your observation actually restricted to a uniform grid, and this actually become the problem of compressive sensing, which was initiated about probably 20 years ago. And there's a lot of nice work associated with it. And there's a vast literature on the theory of compressive sensing and also on various kind of like optimization L1 algorithm associated with it. Now, if the frequency grid and also the sampling grid are not necessarily belong to a Cartesian grid, then this becomes the so-called line spectral estimation problem, which is a well-known problem in electrical engineering and also control theory. And this is also associated with the so-called super resolution problem. So some important papers are this 92 paper by Donahoe, and also Candace et al. Also have in 2014. There's also a very nice theoretical paper. And 2 of the important papers actually in this literature is actually here happened at MIT. One is by Laurent, 2015. And also this by Moitra, also another paper by 2015, also have a lot of nice theoretical results. And line spectral estimation problem is actually an important problem. Many algorithms have been proposed by it. Some of them I will mention today, like the Prony's methods and also Esprit. Various kind of methods has been proposed for that. Now, Laplace inversion is a very hard problem because of the exponential decay rate. So if you have something decay very fast, and if the signal has noise, it's very hard to detect it. In the case of random access, meaning that you're not giving specific sample locations, but you can actually decide to sample wherever you want. This becomes a slightly easy problem. And there's a long literature starting back into 60s working on this problem. Until this day, it's a hard problem. Now, in the equally spaced case, there's also this Prony type methods has been proposed, essentially extending the Prony type of methods in the Fourier inversion case. And as you will see, this is also related somewhat to our work, which I'm going to talk about today. And the last example, sparse deconvolution, also has a long history. In the case of the uniform grid, it becomes a version of the compressive sensing and the super resolution because you can just do a Fourier transform to go back. But somehow, for non-uniform grid, I haven't found a lot of literature on that. But maybe it's not that important for applications. Anyway, so this is a brief overview about this, all the work, all these examples. I'm sure that this is really a very small portion of the paper that has appeared in the literature. So I apologize for this incomplete list. Okay. All right, so in this talk, I'll talk about the general approach to solve this unstructured sparse recovery problem. So the talk will have 3 parts. So the first part, I will talk about an old method, which is called Prony's method. So I will present the method in a way that's try to highlight what I think is the most important thing. And then I will talk about this naming the title called eigenmatrix, which you can view it as somehow generalizing the Prony's framework to this unstructured case for general kernels. And finally, I will present some numerical example, one for each of these 5 examples. Okay. All right. So because, I mean, it's not a big audience, so if you have any questions, please do stop me, and I'll be happy to answer them as I can. All right. So the Prony's method. So Prony's method is a method that has been hundreds of years old. And this is actually addressing a special case of this unstructured sparse recovery problem. By special, I mean that it has a restriction on the kernel and also the restriction on the grid. So the kernel we're going to work on is simply the Fourier kernel, which is gsx is equal to exponential 2 pi I s times x. And the grid, remember, I use Sj to denote the grid. And in this case, the Prony's case, the grid is equally spaced. So for simplicity, let's just take the Sj to be integers. Okay? So, and the data you're given is actually, if you plug this back into the original formula, the data you're given is actually this Fourier kernel evaluated at the integer locations. Okay? It's each exponential of 2 pi I j times xk and multiply weighted with wk. So the idea of the Prony method, as I said, has different presentation, but I'm going to give you a way that I feel most comfortable, and it also connects well with the second part. So in the Prony method, what you do is that you define this vector, which is called bold gx. This is a vector of evaluating this kernel at all the grid points that's given to you. So in our case, because the grid points happen to be the integers and the kernel is the Fourier kernel, so every entry of this vector gx is exponential 2 pi ijx. Okay? And now, we don't really need the data for all the integers, as you will see. But for the purpose of the presentation, it's easier to think about this in the infinite long vector first. It's a vector which indexed by all the integers. Okay? And this vector is actually parameterized by my parameter x. So therefore, for different x, you have a different vector. Now, the second most important thing about the Prony's method is a shifting matrix, this M matrix. So M is a shifting matrix. Essentially, it's shift all the vectors by one slot. Okay? So if you give me a vector v, you apply M. What it does is that in the jth location, it's going to be the vj plus 1 of your input vector. So if you allow me to write a little bit. So this is an infinite dimensional matrix where the matrix M is the infinite by infinite because indexed by integers. And it's really on the plus 1 of diagonal. It has a 0 value, or sorry, 1 value. Everywhere else is 0. Okay? It shifts everything by one slot. Now, why is this important? The reason why this is important is because if you think about applying this shift matrix to this G vector indexed by x, it applies this to G vector. What it does is it shifts everything by one slot. So the jth location becomes 2 pi ij plus 1x. But this is really, because this is a plane wave, so therefore this is really equal to the original vector multiplied by e to the 2 pi ix. So therefore shifting matrix applied to this, my G vector is essentially just corresponding to a multiplication, diagonal multiplication. I'm going to write this way. My shifting operator minus e to the 2 pi I times identity applied to G is going to be equal to 0. Okay? So I'm writing down these matrices explicitly so that you can see what's actually going on. This is quite simple. So what this says is that e to the 2 pi ix is a generalized eigenvalue of this operator, and the G is actually a generalized eigenvector. Now I don't know the location xk yet, sk, but somehow what I said is true for any x. So therefore, m minus e to I xk multiplied the identity matrix applied to gxk is equal to 0. Now, this is not only true for 1k, it's actually true for all the xk's, right? And more importantly, this m minus this shift e to the 2 pi xli, these matrices all commute because they only involve two matrices, m and identity. And m are commutes with identity. So therefore, all these matrices commute. Because they commute, so therefore, I can take all of them, going from the first one to the nx of them. I can multiply that together. That will kill any of these gxk, because one of them will kill it, right? You can do by commutativity, you can move the one actually going to kill it to the end and immediately destroy it, right? So it's equal to 0. Now, here's the time that we should bring our data in, uj in. What I'm going to do is I'm going to take all the uj's and concatenate them into a very long vector, which is this capital U, okay? And each of them is corresponding to the data that was given to me. It's not difficult to see that U is in fact what? It's the linear combination of the gxk vector with weight wk, right? Because this is the linear combination of these Fourier modes, okay? Now, because this product matrix kill each of the gxk, it's actually going to kill the sum of them. So therefore, if you apply this product matrix multiplied by U, it's actually going to be equal to 0, okay? Now, what does this tell us? We need one more thing, which is very important. Because this is a multiplication of m minus constant times identity, and there are nx of them, I can write this as a matrix polynomial, which I denote by Pm. And I denote the coefficient by P0, P1, all the way to Pnx. Now, I don't know the location xl, so I don't know this matrix. So therefore, these coefficients are new to me, and I don't know, I need to work out, solve for them. But nevertheless, I can write them this way, okay? Which means that once you introduce this matrix polynomial, and what we have here is that this matrix polynomial applied to U is equal to 0, right? Now here, I add the matrix together and apply to U. But obviously, what you can do is that you can apply each of the matrices to U and then add them together. That's also equal to 0, right? So here what I'm saying is that apply identity to U, you get the first vector. Apply M to U, you get the second vector, and so on and so forth. So you apply the last matrix to U, you get this one. And then you do a linear combination of them with this P vector with weights given by P0 all the way to Pnx. When you add them together, it's equal to 0. Okay. Now, we know what U is, right? U is this vector. It's the data that's given to us. We know what M is. M is just a shifting matrix. So you see the next vector is just shift everything by one slot. And you keep shifting a couple of times, you get this matrix. And this matrix has a name. It's called a Hankel matrix, because all these anti-diagonals, the function has the same value, okay? And this applies to P equal to 0. Now, this tells us a very important thing about the P, because what is P? The P should actually be the null space of this matrix. And this matrix is actually going to be degenerate, right? It's not full rank. The rank is actually equal to nx. So P is actually the vector pointing at the null space. The magnitude of P doesn't matter. I only need to care about the direction, okay? Because I eventually. So you see that by solving this vector P, by identifying the null space vector of this matrix, Hankel matrix, I'll get this P. Once I have these coefficients, I can plug them back into this polynomial. And now if you go back and take a look, what's the relationship between the polynomial and this e to the 2 pi ix? The roots of this polynomial actually correspond to exactly e to the 2 pi ix. So therefore, once I have this polynomial, I need to find the roots of the polynomial, and this will essentially give me e to the 2 pi ixk. And this will allow me to find out all these parameters, these frequencies. Okay, so this is the idea of the Prony's method. So I hope I didn't bore the experts too much, and at least this is my humble understanding about the Prony's methods. Now, so once you have these e to the weights, sorry, the frequencies, then you can plug back into this relationship which link the weights with the data that was given to me, right? Because now I know xk. All I need to do is solve this linear system to figure out the weights, and then I have this, both the parameters, the frequencies, parameters, and also the weights. And that's a Prony's method. Okay. Now I presented the Prony's method under the case that I assume that all the data is clean. So I don't have any noise. Noise is equal to 0. But if you do have noise, then things are complicated. What you obtain here is actually only corresponding to some kind of approximations, right? They might not be very good approximations. So what typically people can do is that using what you just obtained and use them as initial guess and try to do a little bit post-processing by solving this optimization problem jointly. Now this problem itself is non-convex because this depends on xk, this exponential depends on xk, and xk multiplied by wk, and you have to square it. So this is not a convex optimization problem. But hopefully that you get to a very good initial guess. You go into the local contraction basin. So therefore, you can do a few gradient descent steps or Newton steps, and that will allow you to bring to a better solution. Okay. Now, there's also the problem that what if we don't know nx beginning, right? What if we don't know how many spikes we have? Then what you typically need to do is that you need to generate a slightly bigger matrix and see at what point you have a numerically singular value go to 0. And this is where you cut off. You say, OK, I have 5 modes or 6 modes, depending on the singular value decay. All right, so this is the Prony's method. Any questions about this discussion? All right, yes.
So what can you say about the sensitivity to noise? Like,
it's
like the kind of conditioning.
Yeah, it's a very good question. So even until very recently, I think that the analysis of the Prony methods is a hard question. I think there's a recent paper, which by two, mathematicians with Russian names. I'm sorry, I forget their names. They actually proved that Prony methods up to a constant is actually information theoretical optimal. Yes, but the constant is bad. But I can show. I can point you to reference when I. Yeah. Okay. Okay, so now, limitation of this. Okay, so I want to solve a general problem, right, with general kernel and also unstructured grid. So Prony only solve a special case where the kernel is a Fourier kernel, and also this grid is a uniform grid. And because of these two things, I was able to write down this shifting matrix directly, okay? And it becomes a matrix which has eigenvalues and eigenvectors, right? But this really depends on the fact that the Fourier kernel is a translation invariant kernel. And also the grid I use is a translation invariant grid, right? So without these two things, one cannot write down this shifting matrix explicitly. And without this shifting matrix, I cannot form the Hankel matrix. And then without the Hankel matrix, I cannot solve the characteristic polynomial. Without that, I cannot find the roots. I cannot find the weights, right? So the typical presentation of the Prony method directly starts from the Hankel matrix. But I personally find it's much more important to understand this shifting matrix first. Okay. So the question is that what if I have a general kernel? And what if my grid locations are unstructured? What should we do? So this is this new method which we proposed a while ago. It's called eigenmatrix approach. And eigenmatrix, you will see they're going to play the role of this shifting matrix that I wrote down over there. So the idea is very simple. So in the Prony's method, the shifting matrix is actually very important. It's play a key role. And from a high level, it really turned this into nonlinear inverse problem, this sparse recovery problem, into an algebraic problem, which is through this eigenvalue relationship. And eventually, you just need to go find the roots. Okay. So the idea of the eigenmatrix approach is the following. Suppose you give me a general kernel, or you give me a general sample locations. I'm still going to write down this gx vector as I did earlier. This actually corresponding to evaluating my kernel at all the sampling locations and parameterized by the parameter x. It's important to notice that now this is a finite dimensional vector because I'm only given the data at a finite number of locations, ns of them. And also this as a vector is also analytically dependent on x because my kernel itself is analytic in x. Okay, that's very important as you will see. Now, what I will do is that I want to try to go, the problem is to try to find a matrix M, which now is size ns by ns, such that for all the parameters in my parameter space, this relationship is true. So M, you will see, will also serve roughly as a matrix such that I have gx as my eigenvector and x as my eigenvalue. Okay? And I call this matrix M is eigenmatrix. So I will talk about the two cases, how to do that. One is a complex case. The other is a real case. So let's start with the complex case. This is more elegant. So in the complex case, we assume that, so we record that X is what? Is some kind of open set, right? It's bounded open set. So even unbounded is OK, but it's some open set. For simplicity, let's assume that this is just a unit disk, the interior of the unit disk. OK, this is a unit disk. Recall that the condition for the eigenmatrix is that I want M applied to Gx is roughly equal to XGX. This has to be true for any X on the boundary, in the interior of this unit disk. For numerical reasons, I will scale the vector Gx a bit, because sometimes if you don't have a kernel, if for some kernel, for example, like the Laplace kernel, at some location the kernel is going to be very small numerical value, as other location might have a big numerical value. So numerically, it's not so stable. So therefore, for numerical reasons, what I'm going to do is I'm going to scale all the vectors G's into a unit vector. And then the condition that I want for M becomes m applied to g hat is roughly equal to x times g hat. Okay? Now g hat is normalized. To do that, what we need to do is that we choose a dense uniform grid on the boundary of the disk. I call them A1 all the way to AK. The number of these samples could be hundreds or could be maybe 1,000, or it's not too large, right? Okay. Then what we want to do is that instead of enforcing this condition everywhere in this disk, I only enforce this condition on the boundary, and in fact only on these grid points, the uniform grid points. Okay. Now if you take a look, I can try to write this down, because now I only need to have a finite number of conditions. I can try to write down as a matrix problem. So if you introduce this W matrix corresponding to each of these vectors at all the AK locations concatenate together one by one. So this will be a matrix of size ns, because each of the vectors length ns by NA. Okay? So I don't, yeah. Now I call this W matrix. So these are the matrices essentially have all my approximate eigenvectors. And I also generate the diagonal matrix NA by NA with A1 all the way to ANA on it. These actually correspond to the diagonal matrix has my approximate eigenvalues, right? Once I have these two matrices, this relationship M, this relationship here can be written as MW approximately equal to W times lambda. This is typically, for example, when you're learning a linear algebra class, right? How do you turn the relationship definition of the eigenvector and eigenvalues into a matrix form so that you can talk about eigenvalue decomposition? So therefore, this is the constraint that we need to satisfy. And the solution, numerical solution, actually is pretty easy. It's just I simply set my eigenmatrix to be W times lambda times the pseudo inverse of the W. Okay, so that's essentially the algorithm. Okay. Now, one thing I need to tell you, and these yellow points are corresponding to uniform grid on the boundary of the disk. Now, one thing I need to tell you is that we want to enforce this condition everywhere on the disk. But we end up only enforcing this on a grid which is on the boundary, right? Why is this sufficient? Okay. Now, the reason why enforcing this only at the grid is sufficient is a very simple calculation using Cauchy integral formula and also exponential convergence of trapezoidal rule. So because the reason is because my function gx is actually analytic in x. Because the gx analytic in x, I can use the Cauchy integral formula to write this as the sum on the boundary of gz minus z minus x. This is up. So you can see I put this m here, but without this m is really just a Cauchy integral formula because gx is analytic in x. Now it's a little bit tricky in the sense that because each of the g itself is a long vector, but you apply this Cauchy integral formula for every entry of this vector. Okay. Now the second part we're using the trapezoidal rule, because this is the function which is analytic in z. So therefore on the boundary is actually smooth, right? It's a smooth function on z. Okay. So therefore, so what you do is that this kernel itself is a smooth function. You can, as long as we have the uniform grid on the circle, we can use the trapezoidal rule to approximate it. And this is corresponding to the quadrature weights. Now here you see that only mgak appears. So therefore, I can use this condition that I enforce to write this as a times gak. Now again, a times gak is also an analytic function, so therefore trapezoidal rule is a good approximation. So therefore this can be approximated by this integral, right? I'm turning this quadrature weight back into this integral. And finally, you realize that the gz is an analytic function in z, so therefore zgz is also an analytic function in z. So therefore this whole thing is an analytic function. If I apply the Cauchy integral formula again, this is equal to xgx. And so this is what we wanted. Okay? So it's essentially, this is a very simple complex analysis, elliptic PDE. As long as you check everything on the boundary, and you're fine. Everything in the interior should be true as well. And in order to check things on a smooth function on a smooth boundary, you only need to check at the uniform grid, and the exponential convergence of trapezoidal rule gives you everything. Okay. Now, once we have this, we know that for our general problem, m minus xki times gxk is roughly equal to 0. So therefore, when I multiply them over all the possible, all the spike locations, that's also true. And by defining this u vector as to be the vector containing all my samples, because u is what? It's a linear combination of the xk's. So therefore, this formula is also true. Then the rest is the same as the Prony methods I talked about, right? Because you can expand this as in terms of polynomial. And if you try to write it down, this gives you this matrix equation. And you see that the only difference is that previously I have the shift matrix, shift operator. So therefore, this becomes a Hankel matrix. But in this case, it's not a Hankel matrix anymore because I constructed M. M in general is not a shifting matrix anymore. So therefore, I get a general matrix. But nevertheless, I can also look for its null space. From the null space, I'll be able to have this characteristic polynomial. By finding the roots, I'll be able to find the spike locations. And from the spike locations, I can solve a least square problem to figure out the weights. And if you're not happy with the results, you can post-processing by solving a joint optimization problem. Okay. So the rest is the same. So the eigenmatrix is really replacing this shifting matrix that appeared people using the Prony's method hundreds of years ago with a new matrix that we numerically compute based on the kernel and based on the sampling locations. Okay. Now, so here I give you an example where X is actually corresponding to the unit disk. But we can also work with other domains, right? Because unit disk is maybe too restrictive. And to solve that problem is it's very simple. So let me just draw a picture here. So we have the problem that map from unit disk X to G to S. That's great. But what if I have a different domain X here? What do we do? So this is GSX. What we do is that we use Riemann mapping theorem to map this back into a disk called a T domain, right? And then let's call this phi. And then this composition of this new G tilde X, ST, which is given by G of S and phi T, it's also an analytic function, right? And you see that each of the spike here will correspond to one spike location here. So therefore, we can forget about the middle one first and look for that problem. And to trace back to figure out the spike locations here, and then use map to push forward to find out the spike location in the X domain. Okay? So essentially, this is just using Riemann mapping theorem for complex variables. Okay, I didn't draw a picture. I should have drawn a picture, but yes.
But that's unique, right? I mean, you can have different maps.
Oh, but this map is not unique. But by choosing any map, eventually when you push forward, that actually cancels it. So the location you find here is unique. Right, you can have a different map. Let's call psi, go to T prime domain. You can also do this G tilde tilde double tilde. But so the location here will be different. When you push forward back into X domain, that will land in the same location. Yes.
In the original setup of the algorithm, you have M defined as some kind of multiplication of something with like a pseudo inverse. So
yes, right.
That seems like that's kind of where the problem could lie. Like, can you speak a little bit more about like the pseudo inverse and how that?
So you mean the problem could lie? Meaning
it's not clear to me why this M should exist. This and if W is perfectly invertible, then it's clear. But
no, W would typically not be perfectly invertible because typically the number of samples Sx would be less than the number of points, quadrature points I put on the boundary. So therefore, this is a rectangular matrix. So that's why I use pseudo inverse rather than inverse. And now, so this matrix is defined this way. So it always exists. I can always define it. Yeah. Your question is really why this is accurate, right? Yeah. There's a reason why this is accurate is, well, I don't have a proof yet. But in fact, it's not always guaranteed to be accurate. This very much depends on the property of the kernel. For example, if you're working with exponential kernels, and eventually you will see that reconstruction is actually quite sensitive to noise. And also depend on the sampling points. So if there are sampling points which very much cluster in one region, but I mean, there's only a few other points in the majority of the domain, and that's a bad problem. And my M would be bad. Okay. So I mean, there's a lot of open questions, but that very much depends on how good is the data that's being presented to me.
But M could be good and W ill-conditioned at the same time.
Yes. W you will see will be ill-conditioned. I mean, I can give you an example. W condition number is like 10 to minus 7, 10 to minus 8. But M condition number is like 40. Okay. Yeah, thank you, Laura. Yeah.
So in the original Prony's method, the number of samples you need has to be at least twice the number.
Yes, 2nx plus 1, yes.
How does that manifest here? How does that...
Here is the more sample you give me, the better. Yeah. The more sample you give me, the better.
But where is it even obvious that you need at least, at least twice?
Well, I need to... Well, I mean, for good performance, numerical approximation, for good, error analysis, I think that you will probably need a 2nx in this original Prony's case as well. Yes.
Just information for because that's how many unknowns you have.
Yeah.
But
absolutely, yeah, you're right. That's a good point. Yeah.
But in this case,
typically, the more the better. Yeah.
Right.
Yeah.
We have a polynomial P, and the order for P is D. So is this D known or unknown?
Oh yeah, go. I made a comment earlier. I mean, if you know how many spikes you have, you tell me, great. I'll be grateful. I can work with whatever you tell me. But if not, then you have to take a look at this matrix. You have to take a look at this Hankel matrix, for example. I mean, because of noise, so therefore this matrix numerical, I mean, with probability equal to 1, you will never see a like eigenvalue, just singular value drop to 0. But what you will see is that you will have a big singular values and then suddenly drop to something really close to the noise level. And this is where you cut off. But how to do it? I mean, actually choosing the, I don't know even there's a right way of choosing. I mean, I think there's no consensus. There's a statistics problem, right? But you have to assume certain noise models. Certain criteria to choose is called AIC, BIC, these criteria, which balance the error you make and also the complexity, in this case, how many poles you have, right? So, but this, I mean, I think it's still resolve the problem. But for practitioners, people just take a look at where to cut off, and based on other information you have, you can choose reasonable number of spikes you want. Okay. Now, what about the real case? In the real case, the problem is also similar. What we do is that assume for simplicity the domain is from -1 to 1. And what we want is that we want to make sure m times g hat is approximately equal to x times g hat for any point x inside. But now there's an infinite number of points to check. We cannot check them. What do? Well, we go back to Chebyshev, right? We choose the Chebyshev grid on this interval. So the yellow points correspond to Chebyshev grid. It's clustered towards the end of the intervals, and it's kind of like has a bigger spacing in the middle of the interval. And what you do is that I want to enforce this condition, not on everywhere, but only on the Chebyshev grid. Again, you can write down this condition in the matrix form, and you can take the pseudo-inverse, and that will give you the matrix M in the real case. Now, you can do a similar analysis to convince yourself that, in fact, the checking only at the Chebyshev grid is enough as long as my function gx is analytically depends on the parameters. Here is easy to do, is that because analytic, you can try to write this approximately as Chebyshev expansions, where this are the corresponding to the Chebyshev weights. Now, because this is the matrix applied to vectors, so you can apply matrix to the vector first. But when you apply to the vectors, you get what? You get AKGK, because this is what we enforced, right? And then AKGK itself is also an analytic function, because GZ is an analytic function, so ZGZ is also analytic. So therefore, Chebyshev will be a good approximation. So therefore, this is roughly equal to XGX. Okay, so it's the same proof, even a bit easier. You can also ask the question, what if I don't have a unit interval or the simple interval from -1 to 1? What if I have an arbitrary interval? What if I have a half line? What if I have a curved segment? Well, you can do the same thing as the Riemann mapping theorem. What you need to do is you need to construct a one-to-one map, which pull this X back into the unit domain, right? And then I can redo everything in this unit domain by using this new kernel function. Once I know that what the locations are denoted by zk in the unit domain, I do a push forward to figure out what the location should be on this curved segment or on general domain. Okay. All right. So the rest part of it is I will give you this. I mean, I'm still working on trying to do some analysis, but as I said, the whole analysis, I mean, Laurent knows that, right? The Prony methods analysis is hard. It's not easy. So I don't have too much analysis to report at this point. So instead, I will just show you some numerical examples of the things I've worked on. So the rational approximation. So this is the first example. X is the unit disk, and the spikes are inside, denoted by red, and also the sampling location is outside, which is yellow. So the kernel is 1 over x minus z. And in this example, I have 4 spikes in the domain. And the sampling location is actually outside the disk with the radius with modulus between 1.2 and 2.2. So they are not too close to the boundary of the disk, but they're also not far away. If they're too far away, they don't contain much information because you have this 1 over x decay, right? So they're somewhat far away, which provides you still information. So let me explain the picture here. I have 2 rows. The first row is a simple case where you have the 4 spikes which well separated away from each other. For those of you who work on structure, even sparse recovery problems, you know that when you have things well separated, it's a good case. When you have things really close to each other, that's actually a bad case, right? In the second example, it's a little bit harder. You see that these 2 spikes are get close to each other, so quite close to each other. So this is a easy case, hard case. And different column correspond to different noise level. Here I have 10 to minus 2, 10 to minus 3, and 10 to minus 4 noise. Okay? Does this correspond to standard deviation of the noise I inject into the UJs? Different color coding stand for either the blue stand for the exact solutions, and the green stand for what I obtained using this eigenmatrix methods without before post-processing. You remember I mentioned there's also this joint optimization post-processing step, and the red one is the one obtained after the post-processing. So you see that when the noise is big, 10 to minus 2, and simple case, it works very well. Hard case, it does have an error. For example, these two I got mixed up. But as you move to slower noise, I mean, this actually both works quite well. So in this case, you see that both the green and also the red one actually stay very close to the true exact solution. And in this case, you see that they're right on top of each other. Okay, so when the noise is actually 10 to minus 4, you see that we can do quite well in rational approximation. Okay, so the next example is the spectral density estimation. So recall that the unknowns you want to recover is within the interval from, in this case, from minus 1 to 1. And the Green's function, so this is also, the kernel is a Green's function. And the grid you have is a Matsubara grid, which live on the imaginary axis, which is denoted by these yellow dots. And the temperature, inverse temperature chosen to be 100, so temperature is 0.01. Now I have 4 spikes with the same weight. And again, this is a simple case. You see that the spikes are well separated from each other. This is the hard case where you have 2 spikes are quite close to each other. And again, the noise is from minus 10 to minus 2, 10 to minus 3, and 10 to minus 4. And you see that even in the big noise, we were able to do reasonably well in the hard case. For example, you see that before the post-processing, the location is a little bit off. But when you do a joint optimization, it brings you right to the true location. It's also the case here, and the location is a little bit off before the post-processing, but afterwards, it's actually snapped right to the correct location. And this is even better in the 10 to minus 4 case. Even before the post-processing, it's almost perfect. Okay. So the next example is the Fourier inversion. And we take this kernel to be the Fourier matrix, Fourier kernel, and the frequency is between minus 1 to 1. And the sampling locations corresponding to about 128 locations between minus 5 to 5. And again, this simple case hard case corresponding to where you have 2 frequencies really close to each other. And again, noise is 10 to minus 2, 10 to minus 3, and 10 to minus 4. And you see that quantitatively is similar. And you see that the green one has some location-wise has some error. Also, the recovered magnitude a little bit off. But after you do a post-processing, in all these cases, it works quite well. The next example is a hard case. It's a Laplace inversion. And because of the decay of the Laplace kernel, so it is really a hard problem. So the parameter I choose is from 0 to 2. So this, I mean, in the nicest case, you have no decay, right? Because exponent here, x is corresponding to 0. In the hard case, you have decay rate e to the minus 2s. So it's a quite fast decay. And the low sampling location is between 0 to 10. So there, by you go to 10, I mean, if the rate is, for decay rate is 2, then you have 10 to the e exponential minus 20. So this actually, you don't see the signal at all. Okay. So I put 100 points sampling locations. And again, simple, hard. Simple case, you see all the spikes are well separated away from each other. It's clear to see this picture. And in the harder case, you have 2 spikes which actually get a bit close. It's not very close, but this is really hard problem. Even that is very hard to detect. Now, for the Laplace inversion, I set the noise to be 10 to minus 5, 10 to minus 6, and 10 to minus 7. So for the big noise, you see that the problem is so hard that we do actually face a bit difficulty. So for example, if you take a look at the middle one, when noise is 10 to minus 6, for the easy case, we're able to roughly get the location right, and also the magnitude, I mean, within a factor of 2. And for the harder case, I mean, the location is a bit off. In fact, I try to combine these 2 spikes together. But when the noise goes down, you see actually things get not too bad because we were able to find all these decay modes, and we're able to get the magnitude roughly correct. But I want to emphasize that a Laplace inversion is really, really hard problem. And it's, I mean, if anyone can make any progress on that would be big news. Okay? Inverting Laplace transform is really hard. Finally, we have this sparse deconvolution problem. So, and the kernel we choose is a Cauchy kernel. The center of these bumps were somewhere between minus 1 to 1. and we sample uniformly from -5 to 5. Okay, I didn't show the locations, but it's from -2 to 5 you sample this. And again, this is a hard problem because this is actually a very smooth bump, right? This is a smooth bump, and so therefore, I mean, it's very hard. Deconvolution is really hard. So again, easy problem, hard problem. In the hard case, where you have two spikes which are really close to each other, and noise is from -10 to -2, 10 to -3, 10 to -4, and so you see that in this case we don't do very well, but starting from 10 to -3, 10 to -4, even before and after post-processing, we're able to capture this location also weight quite accurately. Okay, so this is what I want to share with you. In summary, we propose a new method called the eigenmatrix. It's actually a generalization of this shifting matrix which used early in the Prony's method. So I present everything using the Prony's method by finding root, but you can also combine it with methods like music and aspirate, so which does more fancy post-processings for the Hankel matrix. It also works. And we work with general kernel, we work with unstructured samples. And the overall idea is really through this approximate eigenvalue decomposition, you turn a nonlinear or inverse problems into an algebraic problem, which we know how to solve. So this is supported by National Science Foundation, and also this is the preprint I put online last year. So if you're interested, please take a look. And finally, there's a bunch of references about the papers which I mentioned, but what doesn't make sense to go through this. Okay, let me just leave it here. Thank you.